now that we have taken care of introduction to abstract algebra, and we have made 3 videos also on the mathematical foundations of abstract algebra, let's go ahead and talk about a very important structure, algebraic structure in abstract algebra called groups. So we're talking about group theory. So the next 3 videos from this video uh, up to the next 3, right? Like this video, the next one, the one after it will be about group theory. So here, a kind of introduction to group theory. Of course, under the introduction to abstract algebra, we already made mention of group theory and all of that. So 3 things that stand out when we talk about abstract algebra will be groups, group theory, ring theory, and of course, field theory. So here we're talking about group theory, and the first video under that, being the 5th video overall for abstract algebra, is group axioms and examples. Group axioms and examples. So, in this lesson, we study binary operations, the definition of a group, abelian versus non-abelian groups, classical examples like the set of integers, the set of the set of rational numbers, take away zero, and matrices. So, and we'll talk about cancellation laws and the uniqueness of identity and inverses. Okay, so as we step on, let's talk about binary operation. It's a kind of revision again as far as binary operation is concerned, because I think we've talked about it under the foundations of mathematical foundations of abstract algebra. So binary operations, of course, a binary operation on a set S is a function star, such that so an element for S is mapped to S and it gives S. Of course, that is necessary for the sake of closure. That you take an element in S and map it to another element in S, and whatever you end up getting is still that S. And this S now can be any set. It could be the set of integers like Z. It could be anything else. Okay, so this means you can combine any 2 elements A and B belonging to S, and then whatever, if you carry out the operation on it, you still end up getting something on S. So the result A star B is again also in S, and that is the idea of closure that we have talked about before. I mean, this is easy to understand with addition and multiplication when we talk about the set of all integers. So if you add or multiply any 2 integers, you end up getting another integer. So that's a very good example of that. Okay, so let's look at our first example here. Right. So here, example 1, on S equals Z. Okay, that's the example I've just given now. So on S equals Z, that's if the set we are talking about is the set of all integers. Integers are whole numbers, either negative or positive, including 0, which is also an integer. So if you define A star B to be A plus B, so then for any A and B you take from Z, A plus B will also be in Z. So it is a binary operation. For instance, take any 2 random integers, say -7 and 15. All right, and 7 plus 15 is 8. 8 itself is an integer. So take any other one, say 9 and 22. 9 plus 22 is 31, which is also an integer. So anyhow, or if you'd like, take -10 and -21. So add the two together, you have -31, which is also an integer, right? So it works in that case. But on the other hand, example 2. So in example 1, we saw how closure works, and here closure fails in this example 2. Imagine if you now take a set S, which is the set of all natural numbers. So natural numbers are normal counting numbers. So if I say you should count now, just go ahead and say 1, 2, 3, 4, 5, and so on. That's why they are called natural numbers. So on the set of natural numbers, now define A star B to be A minus B, for instance. So if you take in this case, it is not guaranteed that if you take any 2 natural numbers and you subtract them, and you carry out this operation of subtraction on them, you get another integer, and I mean another natural number. That's not always true. It is true in some cases. For instance, if I say 2 minus 1, you get 1, which is also a natural number. If I say 3 minus 2, you get 1. If I say 4 minus 3, you get 1. If I say 5 minus 2, you get 3, which is also a natural number. But imagine if you take A to be 2 and B is 5, then 2 minus 5 is -3. So 2 minus 5 is an integer, but it is not a natural number, right? So in this case now, subtraction is not a binary operation on n, right? So maybe addition can be, because if you add 1 and 2, you get 3. If you add 10 and 20, you get 30. which is also a natural number. So subtraction is not a binary operation on natural numbers, whereas addition is a binary operation. Of course, addition will be a binary operation here. To also be a binary operation for a set of integers. So let's look at example 3, which also works. So for example 3, now we are saying that the set S, which we talked about for binary operation, is Q take away Q star. Anytime you see Q star, it means Q take away 0. Q is a set of all rational numbers. So any number you can express as the ratio of two integers is said to be rational, right? So this one is a larger set that contains almost every number you can think of. So it's something like 0.2 is rational in the sense that you can express 0.2 as 2 over 10, which is 1 over 5. So but of course, we take away 0 because what's about the possibility of dividing by 0? So that's why we have to take away 0. All right. So that's Q star. So on that now, if we define A star B to be AB, so if A and B is not 0, right, then of course AB will never be 0 because you have taken away 0 already, right? And AB is always an element of Q star. So if you pick any two rational numbers, say half and 4 over 3, right? Half and 4 over 3. If you multiply half by 4 over 3, you get 2 over 3, which is also another rational number. So in this case now, this operation of multiplication is a binary operation on the set of all rational numbers take away 0, right? So now that you have taken the idea of a binary operation out of the way, now that was a necessary thing to talk about because a group, when we talk about since we are talking about group, a group is about a set and a binary operation. And of course, one of the previous videos is about sets, right? Where we talked about sets, set, subset, and power set, right? So now we know about sets. We know a set is a collection of well-defined items, well-defined members, well-defined objects without repetition. And now we know a binary operation. So these two ideas of set and binary operation come together when we talk about group. So definition of a group. So a group is simply a pair, G and star, where G is a set and star is a binary operation on G, which now follows the following axioms, as we already saw under Introduction to Abstract Algebra. But here we are going deeper into the whole thing, right? So a group is a pair G, comma star, where G is a set and star is a binary operation on G, such that closure is obeyed, meaning that if you pick any two elements A and B in G and you carry out of course the binary operation will be defined each time you need it, right? So and you carry out the operation on it and you get the result you get is also in G. Then that's the first condition. That's closure. Associativity is also there. So for all A, B, and C, any three elements you pick from the set G. So if you carry out the operation, if you do it on A, B first before doing it, whatever you get from A, B, you now do it with C. You get the same result as when you do it on B and C first before you now do it with A, right? That is the idea of associativity. Then there's also identity. We've talked about this also previously. So there exists a particular element E which belongs to G such that for all A you take in G, for any element you take in G, so if you do the operation with the identity, or you do the identity with the operation, you always get that A. All right. So for any A you pick, A star A is A and A star E is A. Also, I gave very good examples about the additive identity and multiplicative identity. The additive identity, we take that to be 0 because anything you add 0 to, or anything you add to 0 will always give you that thing. So whenever you add 0 to something or you add something to 0, it will always give you that thing, right? And for multiplicative identity, I talked about the fact that 1 is a multiplicative identity because anything you multiply 1 with, or anything you multiply with 1 will always give you that thing, right? So so anytime you multiply one with something or you multiply something with one, you get that thing. That is what I meant to say. So for inverses now, for each A which belongs to G, there exists A inverse belonging to G such that A star A inverse equals E. That is, if you carry out the operation on a particular member or a particular element of G and the inverse of that element, the answer you get is the identity. Or if you also say A star star A star, I mean A inverse star A, you also get the identity. So I also gave the example there that for addition, right? The inverse is always the negative of whatever number you start with. So if you have -1/7 under addition, the whatever you add, you need to add to -1/7 to get 0 is the inverse. So for -1/7, the additive inverse is simply +1/7, because -1/7 plus 1/7 is 0. Or if you say 10, all right, so that 10 is positive, right? So for you to get 0, you need to add -10 to it, or subtract 10 from 10. So that means the additive, the inverse of 10 is -10. And when you come for multiplication, you have 3/4. So to make so you want, what can you multiply by 3/4 to get 1? That's 4/3. So you say 3/4 is the inverse of 3/4 under multiplication. So that's what inverse is all about. So let's look at some examples. So we have this example with the with the set of all integers under addition. So we say that the set of all the group consisting of the set of all integers plus the operation of addition is a group. How do we prove that? So let G be equal to, so our set now is the set of all integers, and the operation star is addition, right? So we prove closure. So closure tells us that for any two integers you pick and you add them together, the result you get is always another integer. So I talked about that before. For all a and b in the set of integers, that's that. Then for associativity, since we are talking about addition, pick any three integers. If you add them together, like 3 plus 4 plus 5, 3 plus 4, 7. Okay, maybe okay, I may have to use numbers to talk about these things as we go on. So a plus b plus c is equal to a plus b plus c. Like a plus b first and then plus c, or b plus c first and then plus a for all integers. That also works. So for identity, the identity is 0 because 0 plus a is equal to a plus 0, and that is a, right? And for the inverse also, for the inverse, for a belonging to z, the inverse is -a because a plus -a is 0, right? So we have all of that. I think I've done examples around this. I'm thinking I should, just explain with some numbers. Let's see. Okay, so for if because all of these things are obeyed now, we can say that z, the group consisting of the set of all integers under addition, is a group. So you can now check. If a is 7, for instance, then a inverse is -7 because 7 plus -7 is equal to 0. So uh let's do this on the worksheet to show, want to show that uh the group of all integers under addition is a group. Okay, so that's what we want to show. So we have to start one after the other. First of all, let's take closure. So for closure, right, uh we need to show we need to show we need to show that for all AB belonging to Z, okay, A plus B is always also belonging to Z. So we can take examples like, imagine, just take two, let's take 2 and 3. So we say 2, if A is 2 and B is 3, for instance, 2 plus 3 is equal to 5, which is also an integer. These two they are all integers, right? So that's one thing. That's so close. So, and you can never find any situation where you take any two integers, and when you add up the two integers, you don't get another integer. So if you can find one case, then you can say that the operation addition is not closed for on the set of all of integers, right? So that's that. So then we go again for number 2. We've talked about closure. Then now we talk about associativity. Associativity. Okay. So for associativity now, so we need to show that A, B, C belonging to for okay, let me use the notation. This means for all ABC belonging to the set of all integers, right? A plus B plus C, A plus B in bracket is equal to A plus B plus C, B plus C in bracket. So let's take let's take an example for that. So imagine A is 2, B is 3, and C is 4. So we now have 2 plus 3, 2 plus 3 in brackets plus 4. So 2 plus 3 is 5. 5 plus 4 is 5 plus 4 is 9. Okay, we have that. Apart from that, we now have 2 plus 3 plus 4. 3 plus 4 in bracket, that's 2 plus 3 plus 4 is 7. That's also 9. So you see that that's true, all right? So just like we checked closure here, so uh, so we can, let me just say closed. Okay, I'll just say closed. That's what that means. And since these two answers are the same here too, I can say the operation star is associative. It is associative. We have that. That's number two. For number three now, the third one, right, is we need to talk about identity element. Identity, identity. So for identity now, we need to show, all right, that for all a belonging to the set of integers, right? A plus a plus there's something such that a plus 0 is equal to something plus a, right? We need to be able to show that, right? And I'm thinking of the best way to show that. Okay, we need to show that a plus something is equal to something plus a, and that is always a, right? How do we say that? Let's assume that that thing is x. Let's say it is x, right? So you can pick either of these two, you get the same result. So we have a plus x is equal to a. That implies that x is equal to a minus a. So x is equal to 0. So under addition, 0 is the identity element, right? Because, or if you like, if you go the other way, it's still the same thing, right? So if you say x plus a equals a, that still implies that x is equal to a minus a. So x is equal to 0 still. So the identity element, so we can say, so the the identity element for addition is 0. What does that mean? That means that if you add 0 to anything, or you add anything to 0, you get 0. I mean, you get that thing, like I've always said. So, so we can take an example. If you say, let me take any number, say minus 1 over 10. Okay, minus 1 over 10 plus 0 is equal to 0 plus minus 1 over 10, right? And that is always minus 1 over 10. So 0 doesn't seem to have any impact on it. So that's the idea of identity now. So this is about a very scientific way of getting that 0 out, right? So that's, so the three conditions. So now we see that there's identity element, right? So I can say identity element exists. Identity element exists. Okay, so three conditions met. So if one of these conditions fail, then so we cannot say z comma plus is a group. So the last thing is inverse element. Inverse element. And what do we need to show here? So we need to show, all right, that for all a belonging to the set of integers, because that's the set we are dealing with. So we actually have a a a s- a star. I mean, we actually have a plus a inverse, which is equal to a inverse plus a, and that is always equal to 0. I mean, yeah, it's always equal to 0 because 0 is the identity element here. It's equal to E, right? The identity element, which is 0 for addition, right? So you see, we have these possibilities now that A plus A inverse is equal to 0, right? Or better still, we have anyone you pick. Let's pick this one like this. So we are looking for this A inverse now. So if you go ahead and work with this the way it is, so we are looking for A inverse. So A inverse, you have to subtract A from both sides. So you have A inverse equals 0 minus A. So A inverse is equal to minus A. So in short now, we see that the inverse, so the inverse of A is always, the inverse of A is always minus A. So let's take an example. So we have an example. Let's take the minus 1 over 10 I just did now. So imagine you have minus 1 over 10. So what will you add to minus 1 over 10? Or what will you add minus 1 over 10 to? All right, to get 0. That's the question we're asking here. And the question, and that is simple. So if what we have is minus 1 over 10, right? So you need to add minus 1 over 10 to it to be able to get 0, basically. So because that should be minus A. So A is minus 1 over 10. So if A, all right, maybe I can say that A if A is minus 1 over 10, then my A inverse will be minus A, which is minus 1 over 10, and that is equal to 1 over 10. So if you add 1 over 10 to minus 1 over 10, you get 0. So that means you have, so back here now, you have minus 1 over 10 plus 1 over 10, and that is 0. So again, you say, this is, so you can say inverse element exists, inverse element exists. So you can do the same thing. Your inverse element exists. So overall, you can then conclude overall, the group of containing the set of all integers under the operation of addition is a group. It's actually a group because it obeys all the conditions of closure, associativity, identity elements, and inverse, like that. Okay, let's come up and talk about another example of Q star with under the operation of multiplication being a group. So we already know Q star is actually the set of all rational numbers take away 0, right? For obvious reasons. So let the group now, the set be Q star, which is equal to Q take away 0, and operation be multiplication. That's what this when you see dots, that's multiplication. So for closure now we have AB. So AB, so for closure, if any A and B you take from Q star, and then AB itself, when you multiply A and B, you always also get something in Q star. I made mention of that before. For associative now, if you have ABC equals ABC, so AB bracket C or A bracket BC, you get the same results. Then the identity, we see the identity here is 1. So here you have 1 dot A is A and A dot 1 is A. Then the inverse for A belonging to Q star, the inverse is A inverse, which is 1 over A, and 1 over A also belongs to Q star. So Q star with under multiplication is a group. So the worked example, if A is 3 over 5, then A inverse is 5 over 3, and 3 over 5 dot 5 over 3 is 1. Okay, I think I want to do the same thing I did for addition the other time on Q star under multiplication. Of course, don't forget Q star is all the set of all rational numbers take away 0. Okay, so we want to show that Q star under multiplication is a group. All right. So again, we take the conditions one after the other. So we start with closure. Okay. Want to check if it is closed. So of course, as usual, we need to want to show that. Uh, so want to show that for all A and B belonging to Q star, all right, then A dot B is also belongs to Q star, basically. So what do we do? Let's pick two possibilities, right? Let's say, yeah, as usual, let's pick any two random rational numbers. So let's pick say 5 over 7, all right, and say 2 over 3. Okay, let's pick that. So let A be 5 over 7 and let B be 2 over 3. So now this implies that A dot B is 5 over 7 times 2 over 3. That is simply 10 over 21. And 10 over 21 also belongs to Q star, right? 10 over 21 is a rational number also, because a rational number is simply a number you can write as a ratio of two integers. 10 is an integer, 21 is an integer. So that's a rational number. So closure checked, right? So we move on to associativity. Associativity. So for associativity now, what do we do? Show 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 that show that for all A, B, C belonging to Q star, all right, belonging to Q star, A dot B, A dot B in brackets, all right, dot C is the same thing as A dot then B dot C in bracket now. So that's all we need to show there. So what do? Pick any three. Okay, so let's imagine we pick say A is 1 over 4. This is an irrational number because 1 is an integer, 4 is an integer. B is say 2 over 5. Okay, this is also a rational number because 2 is an integer, 5 is an integer. And we pick C to be, say, whatever. Let's say 3 over, say, 8 now. Okay, so these are the three numbers now. So we now do 1 over 4 dot 2 over 5 first, then dot 3 over 8. That means for this one now, 2 here is 1, 2 here is 2. So we have 1 over 10 multiplied by 3 over 8. That's simply 3 over 80. Of course, this is 3 over 80, which is also, I mean, established that it's also, of course, this is also in Q star. All right, it's clear, it's in Q star, it's a rational number. So we've done that. So next we have 1 over okay, we have 1 over 4 outside the bracket now times 2 over 5 times 3 over 8. So what do we do here? So 2 here is 1, 2 here is 4. So we have 1 over 4 times 3 over 20. So again, 1 times 3 is 3, 4 over 20 is 80. And that's also in Q star, right? But the most important thing is that this and this are equal, okay? The two of them are equal. So what do we say? Uh, Associativity checked, okay? So it is associative. Then the next thing we go for identity. Identity. So we go for identity, right? So what do we need to show here? So here we need to show that for all any A at all belonging to Q star, all right, there's actually something like that's an identity. Say there's always something, there's an identity that oh, what's identity again? Have I forgotten that? There's an E, right? Such that, okay, let me confirm that. How did I forget? So yeah, on the general note now, identity. Okay, there's something plus a. Okay, I'm looking at the general case now. Okay, there's actually an E belonging to G such that for all this now. Okay, good. All right, so let's go back. So we want to show that for all A belonging to Q star, there's actually an E belonging to Q star also, all right, such that E E dot A is equal to A dot E, and that is always equal to A. Okay, so now we need to find this identity element now. You need to find that. And you can pick any side you like, pick anyone you like to do that. So let's see. So in this case now you see um E dot A is equal to A. That means that to get E, we are looking for E now. To get E, you can divide through by A. So you have E dot A all over A equals A all over A. So A cancels out. So E is simply over A. That is 1. So if you also take it the other way around, if you do A dot E equals the same thing, divide through by A. Okay, so if you divide through by A, you see that E is also equal to 1. So in this case now, we can conclude. So the identity identity under multiplication is 1 easily. So it's 1 like that. Okay. So with that in place, we have so we can check identity checked. So let's move on to inverse. So we'll talk about inverse elements. All right, talk about inverse elements. Okay, we always like to use this for example. So let's talk about inverse now. So we have checked closure, associativity, and identity. So let's look at inverse now. What do we need to show here? Show that for all A belonging to Q star, okay, there exists a particular there exists a particular A inverse which also belongs to Q star, all right, such that such that A dot A star, I mean A dot A inverse is the same thing as A inverse dot A, and that is always equal to the identity element, which you have found now to be 1. Okay, so let's find that identity element. So we know you can pick any side you like, anyone you like, and equate it to E. Or you can pick this and equate it to the same E, anyhow you want it. So anyhow you want it, you get the same result. So you have A dot A inverse equals E. Of course, E is 1 under multiplication, as we found here already. That's what we found here to be our E. So now you have A dot A star, A inverse rather, equals 1. So you're looking for this A inverse. So A inverse uh is equal to 1 over A, right? So basically, so the inverse, you can conclude that the inverse of A is 1 over A under multiplication, all right? Under multiplication, all right? So with that in place, then yeah, you can take some examples and do all of that. So basically, if you have okay, I didn't use numbers in this case. Okay, I used numbers up here. So here I didn't bother because we okay, I mean if you want to do an example here, right, you can then come and talk about it. Like if you want an example here, so it means if you have, let's take any rational number, say you take 3 over 8. 3 over 8 times 1 is the same thing as 1 times 3 over 8. And that is 3 over 8. That means that 1 is actually the identity. For the inverse now, if you are talking about 3 over 8, so if you take an example of 3 over 8, so you see 3 over 8 times something is equal to that something times 3 over 8, and that is always equal to the identity element 1. Of course, you and I know that that should be 8 over 3, because that will be, so we know that this now, this whatever this is now is going to be the inverse. That'll be 1 over 3 over 8. And 1 over 3 over 8 is simply 1 times 1, or if you like, I mean, I'm just trying to be finicky here. 1 divided by 3 by 8, which is 1 times 8 over 3. That's 8 over 3. That's the inverse of that, as we found already. So it means that you need to multiply 3 over 8 by 8 over 3, to get 1, because 8 cancels 8, 3 cancels 3, so you get 1 right there. So you can conclude, so so the collection of set Q star is all rational numbers take away 0 under multiplication is a group. So if any of these conditions should fail, then it ceases to be a group. Okay, so let's move on now. Having talked about groups, let's talk about matrices. And the question here is, why invertible matrices form a group? Why do invertible matrices form a group? So an invertible matrix is a matrix that has an inverse, right? So let GL sub n of R be the set of all invertible n by n real matrices under matrix multiplication. So it will always obey closure. The product of invertible matrices is invertible, sure thing. Then associativity, matrix multiplication is associative. So any order in which you do the multiplication, you get your result. Then identity, now the identity matrix I, right? So inverse, so the identity matrix, for the identity for a matrix is I. I think I'm going to do the example. Then you have the inverse for every A belonging to this set of all invertible n by n matrices. That's square. Of course, you can only invert a square matrix. Has an inverse AL also belonging to the invertible n by n real matrices. So GLN, so GL sub n of R with under multiplication is a group. So important, the set of all n by n matrices is not a group under multiplication, because singular matrices do not have inverses. So not the set of all n by n matrices, but the set of all invertible. So the word invertible is extremely important in this case. So let's look at some possibilities, right? So example, inverse of a 2 by 2 matrix. So let A be 1, 2, 3, 4. Compute. Okay, I guess I want to go. So you can verify A inverse is I, and A inverse A is also Y by multiplication. Okay, well, I think I want to I want to do this. Yeah, let's go ahead and do this. So I'll do the same thing I've done. It's only going to take a bit of time, but it's okay. So want to show that GLN of R. So the set of all invertible real real matrices, right? Is with under multiplication is a group. Okay, so let's go for that. We've been doing things like that, but let's talk about matrices too in this case. So let's go for this to show to show to show that the collection GLN GL sub n of R with the operation multiplication is a group. Of course, we already know GLN of R. This simply means that this means we are talking about I guess I want to change the color here. Let me bring in this person. It's been a long time. So to show that GLN, so the GLN now is all 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 um invertible, all invertible, okay, real matrices. Okay, all invertible n by n real matrices. Okay, on with under the operation multiplication is a group. So let's go. How do we prove that as usual? So first of all, come and talk about closure. So if you pick any two invertible matrices, of course, for a matrix to be invertible, its a determinant must not be zero. So we know we can quickly find determinants, especially if you take a two by two matrix. For closure now, we want to show. So here to prove closure, we just need to show, right? Show that for for all, so we want to show that for all matrix A and B, which belong to GL sub n of R, okay, is okay for all of that, right? AB is also a set, but also belongs to GLN of R. Okay, that's all I want to show here. So let me just take two easy matrices. Say A is equal to 1, 2, 3, 4. All right, A is 1, 2, 3, 4. Of course, this one easily is invertible. Just check the determinant. Determinant is multiply the uh the determinant is 4 times 1 minus 3 times 2. Okay, that's 4 minus 6, that's minus 2. Okay, so this is invertible. So it means it fits the criteria. Then we can also come for B. Say B now is 1, 3, 4, 2. I mean, this is me just switching things around. So this one still has a determinant. That's 2 times 1 minus 3 times 4. Okay, that's 2 minus 12, which is minus 10. So this one is also invertible. So if we multiply these two now, will it also be invertible? That's what we're saying. So now AB now is the real deal. So we have 1, 2, 3, 4 multiplied by 1, 3, 4, 2, 1, 3, 4, 2. Okay. Now, and if you've ever followed any of my matrix videos, I have a smart way of doing this. So first of all, this is a 2 by 2 matrix and this is a 2 by 2 matrix. It means you can multiply them and you also get another 2 by 2 matrix. All right. That's established. So we can actually go ahead. And before you do that, the next thing is forget about the first one. Focus here first. Now, this one has okay, so if you focus on this, but then what do you need to do? You need to write 1, 4, 3, 2. You need to write them a number of times. The number of times you write them will determine on the number of rows here. And the number of rows here is 2. Okay. So since the number of rows is 2, so it means you have to write this 1, 4 twice. 1, 4, 1, 4 twice. And then 3, 2, 3, 2 also. You write them twice. Then you now bring these ones. This 1, 2 now. You now write it twice, you write it twice over the one you wrote before. 1, 2, 1, 2. Then, of course, this one also 3, 4. You write it down here. 3, 4, 3, 4. Or maybe I should color code so you can really understand what I'm talking about. So let me come for this now. So um, let me do this. So 3, 4. You now write it over this 3, 4, 3, 4. That's second row. Okay. So all you just need to do now is to add things together and you'll be good. So here now, 1 times 1 is 1, 4 times 2 is 8, 8 plus 1, 9, right? 2 times 2 is 4, 3 times 1 is 3. That's add the 2, you get 7. 1 times 3 is 3, 4 times 4 is 16, 16 plus 3 is 19. Then 3 times 3 is 9, 2 times 4 is 8, 8 plus 9 is 17. Okay, of course it's glaring that this one is invertible because the determinant is also not zero, because 9 times 17 minus 19 times 7 is not zero. Okay, so here now we see that the determinant AB is not zero. Okay, so uh so uh so closure 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 exists. Maybe let me just put it that way. Closure exists. Done. Okay, that's the first part. So for the second part, that may be that will be a bit messier, but it's okay. I'll just pick very easy matrices in this case now. So for associativity, now, associativity. So what we need to show here is that one here we want to show 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 that for all for all a for all matrices A, B, and C belonging to GL sub n of R. Is that how it's written though? That sub n is looking strange to me. Yeah, okay, we're good. All right, it's fine. So for all show that for all or for every A, B, C belonging to GL and R, then if you like, you have A dot B first multiplied by C. It is the same thing as A dot then B dot C like this. Okay, this is going to be tedious, but it's okay. I'll pick very easy matrices. So let's go for, let's say A is 1 0 0 2, and then B, I mean this one has a determinant, thankfully. Then B is say 1 1 1 1 1 1 0, in fact, and then C is say 1 2 0 1. Okay, let's have it this easy. Wow, this is going to be a lot, but it's okay. So first of all, we need, so if we want to, so for A dot B dot C with AB coming first, so we have 1 0 0 2 into 1 1. All right, 1 1 1 0. So we can easily have that to be, as usual, just have 1 1, two rows here, 1 1 1 1, then 1 0 1 0, then invert this over it, this now. So you have 1 0 1 0 here, and here you have 0 2 0 2, and in one blow we can get all that. 1 times 1 is 1, this is 0 down here, so this is 1. 1 times 1 is also 1 there, so this is 2 here, and this is all 0 right here. Okay, so that's AB like that. So if we now do A dot B dot C now, so it means we have 1 1 2 0 into C. C is now 1 2 0 1 1 2 0 1. Okay, again we can easily do that. So write this twice. So write this twice, and 2 1 also twice. So 1 0 1 0 2 1 2 1. Then invert this over it again. So 1 1 1 1. And here you have 2 0 2 0. So in one blow, we get AB dot C also. 1 times 1 is 1, the other one is 0. So this is 1 here. 2 times 1 is 2, 1 times 1 is 1. That is 3 if you add the 2. 1 times 2, that's 2. 2 times 2, that's 4. Okay, so we see now, we can say, so A dot B dot C is equal to 1 3 2 4. Done. Okay, so we now go for A dot B dot C. Okay, so for A dot B dot C. So it means B dot C first before you now do it with A. So, so B dot C, so here we see that B dot C is equal to, what is B? B is 1 1 1 0, 1 1 1 0, and C is 1 2 0 1, 1 2 0 1. So again, we can do the smart thing. So 1 0 twice, so you have 1 0 1 0, 2 1 2 1, and we put 1 1 over it. So we have 1 1 1 1, and then 1 0. You have 1 0 1 0. So multiply out. 1 times 1, there is 1. This is also 3. Then 1 times 1 is 1 here, 2 here, because 0 is the other one. So we now have A dot B dot C. So our A is 1002. Okay, so A is 1002, and that is multiplied by B dot C, which you just got as 1312. Again, do the smart thing. So you have 1 1. So this 1 1 twice. Okay, then 3 2 also. twice. 3, 2, 3, 2. And then you can invert this over it. 1, 0, 1, 0, and then 0, 2 now. You have 0, 2, 0, 2. So get that out. You have 1 times 1 up there, 3 times 1 there. So 2 down there, and this is 4. So 1, 3, 2, 4, right? Just like what we got before, 1, 3, 2, 4. So you see 1, 3, 2, 4, 1, 3, 2, 4. So you can say, so A dot B dot C is equal to A dot B dot C. So what do we conclude? So associativity exists, if you like to put it that way. So the full way to put it is that, so the operation of multiplication is closed under the set of for all sets of uh invertible real integers. That's actually the long form of how to express what has happened here. So if I say associativity exists, that's actually the long way to say it. Okay. So now with all of that in place now, we have taken care of closure and associativity. Now let's talk about um identity element. Let's talk about identity element. How do we go about this? So for identity element, it's still the same idea like before, except that now we are dealing with matrices. So right. So for identity, right? Identity. So what we need to show here is, so we want to show that for all matrix A belonging to GL sub n of R, like that, okay? Um there exists a particular identity element, which we call I in this case now. So it's called I instead of small a. So I, which also belongs to G, L, N of R, okay, such that, such that, such that A multiplied by I is equal to I multiplied by A, and that is always equal to A, right? So that is the big deal here. And how do we find, so we are looking for this I now. We're looking for this I. Of course, well, if you just want to follow it the way it is here, you have A dot I is it AI is A, right? So, and since you are dealing with matrices, you cannot just divide through here now. So you have to do some kind of cancellation. We are going to find out about cancellation more later. So here now we're saying that oh, did I say I? Sorry, sorry, sorry. Uh okay, yeah, there is an element I such that A dot I. Okay, yeah, I think it's fine. Let's put it this way now. So we don't know what this I is. Okay, I think it's better. Let me just use the normal E before. Okay, let me use the normal E. That way to make sense. So we can actually find that E. It will end up being this I, sorry. Yeah, so there's a particular E, which is the identity element such that A dot E is equal to E dot A equals A. So if you now pick any two of this, so if you pick this or this equals A, so let's say AE equals A. So if you want to find A, now how do we go? We have to, we can't just divide through by A, now we have to multiply by the inverse. Well, I mean, we have not come across the idea of inverse, but that's the way to go actually. Or if you want to do it crudely, you know, um, so so here now you have A divided by E all over A. Let me do it the crude way since we have not come across the idea of inverse before now. So this cancels out and we have E now to be A over A. It is supposed to be 1, but since we are dealing with matrices, we don't call it 1, we call it I. Okay, so I is the identity matrix. So I is the identity matrix, right? The identity matrix of the identity matrix for A, right, which belongs to GL sub n of R. Okay, so the only thing we can do now is to look for a practical example. So yeah, let me use one of the easy matrices I've used before. So let's say matrix A 1 0 0 2. So for A, which is 1002. So we want to see what does I look like actually? What does I really look like? So watch out for this. Or let me just use something more serious. Let's see. Do we have one that is a bit more serious than this? Okay, let me even do 1, 2, 3, 4 like I did before. We can even still do 1, 2, 3, 4. So let's say for A, which is 1, 2, 3, 4, let's do A, which is 1, 2, 3, 4. We are looking for I now. So we know that A times I is equal to I times A, and that's always equal to A. Okay, so if you have it that way now, so what are we doing? So we have now that so we want to see what that I looks like. So we know that AI is equal to A. So that means here we have oh, there's no how I wants to talk about inverse. This is 1, 2, 3, 4 multiplied by I equals 1, 2, 3, 4. So if you just multiply through, if you just divide, we get 1. But what is that 1? What does 1 mean in this sense, right? Um, can I do this? Okay, what I'm just going to do is for us to take care of this now, we are going to talk about an inverse later, right? So, but let me just jump the gun. So 1, 2, 3, 4 inverse multiplied by 1, 2, 3, 4 inverse. I mean, multiplied by 1, 2, 3, 4 I is equal to 1, 2, 3, 4 inverse multiplied by 1, 2, 3, 4. So this way now, this one cancels this out. But in reality now, what does this translate to? So what I'm going to do is I'm just going to compute the inverse of 1, 2, 3, 4. Let me use Wolfram Alpha and compute the inverse of 1, 2, 3, 4 so that I won't waste time with that. So Wolfram Alpha, that's one of the tools you can use for quick things like this. So I just want to do the inverse of a matrix. So inverse, so I want to look for the inverse of matrix like this. Okay, so imagine I just need a matrix. I just need the inverse of 1, 2, 3, 4. So I just pull this. So I have 1, 2, 1, comma 2, then this now 3, comma 4. I'll just go straight for that. So the inverse is simply minus 2, 1, 3 over 2 minus half. Okay, minus 2, 1, 3 over 2 minus half, minus 2, 1. This is so this inverse now is minus 2, 1, 3 over 2 minus half. So if you find the inverse of this is what you get. So you don't have 1, 2, 3, 4. So you need to multiply these two together. So I actually want to bring out the idea of identity for this one now. So if you multiply out again, so you have 1, 3, 1, 3 because this one has two rows here. So 1, 3, 1, 3, 2, 4, 2, 4. Then you now put this one over the top. That's minus 2, 1, minus 2, 1. Then 3 over 2 minus half. So you have 3 over 2 minus half, and then 3 over 2 minus half, like this. This one can be a bit messy, but please follow. And this is equal to 3 times 1 is 3. 1 times minus 2 is minus 2. So 3 times minus 2. So here it's like you have 3 minus 2 right here. Then up here you have 4 minus 4. All right, 4 minus 4. Down here you have 3 over 2 minus 3 over 2. Interesting. 3 over 2 minus 3 over 2. And down here you have 2 times 3 over 2. That's 3. All right, minus 4 times minus half, that's minus 2. Okay, there we get our answer. So I is equal to 3 minus 2 is 1, 4 minus 4 is 0, 3 minus 2 minus 3 over 2, that's 0, 3 minus 2 is also 1. So this is the identity element for a 2 by 2 matrix now. So generally speaking, so this is for a 2 by 2 matrix. So we can say that I for a 2 by 2 matrix, that is 1, 0, 0, 1. So if it is the inverse for a 3 by 3 matrix, that will simply be 1, 0, 0, 0, 1, 0, then 0, 0, 1. So for the leading principal diagonal now, running from left to right, all the elements will be 1. That's what an identity element looks like for a matrix. Okay. So that's us proving, I've been showing the identity, that identity exists. So I can conclude here that identity exists. Identity exists. So what this simply means is that anytime you multiply a matrix by its identity, the matrix remains the same. Maybe we can quickly check that even. So check, you have matrix A, which is 1, 2, 3, 4, and then you have identity, which is 1, 0, 0, 1. So if you multiply out, so if you have AI or IA, anyhow you want it, you have 1, 2, 3, 4 multiplied by 1, 0, 0, 1. What happens? 1, 0, 1, 0, 0, 1, 0, 1, and then you have 1, 2 on top of it like that. So 1, 2, 1, 2. And this is 3, 4, 3, 4. So if you multiply out, 1 times 1 is 1, then 2 times 0 is 0, so that's 1. 0 times 1, 1, 1 times 2, 2, 1 times 3, 3, 3 times 3 plus 0 times 4 is 0, so that's 3 here. 0 times 3 is 0, 1 times 4 is 4, and that's it. So you see that AI or IA is always A. So that's why I is the identity element. So that's a long one for identity. Let's talk about inverse quickly, since that's what we are about. Okay, so for inverse now, so talking about inverse, what do we want to show here? So want to show that for all A, okay, let me use big A now. For all A belonging to GL sub n of R. So that GL sub n of R is the set of all invertible n by n real matrices. So that's what that is. To show that for all A belonging to that, there's actually a particular A inverse, all right, belonging to GL sub n of R, such that A dot A inverse is equal to A inverse dot A, and that is always equal to the identity element. So, that's a sweet way of looking for this. So we can give an example. Okay, give an example. So we want to find uh what the A inverse may look like. So if A is 1, 2, 3, 4, okay, then what we are looking for A inverse. A inverse is what we are now looking for. So we already know that okay, we already know that A inverse is always equal to the identity element I. For a 2 by 2 matrix, we know that'll be 1, 0, 0, 1. So we already know A to be 1, 2, 3, 4, right? But let A inverse be A, B, C, D. Let the elements of A inverse be A, B, C, D, right? So that means that I itself, which is 1, 0, 0, 1. So if you have it this way, we can find the elements of the A inverse here now. So because this is A now. This is A inverse, which you are looking for, and this is I. Okay, so we are looking for the elements here. So what happens? We can multiply this out on the left-hand side. So here we just have AC, AC, these elements now. Because there are two rows there, we have AC, AC, and we have BD, BD. So for AC now, this is 1, 2, 1, 2. And for the other one, we have 3, 4, 3, 4. And all of this now is equal to 1, 0, 0, 1, right? So that if you multiply all this out, you have A times 1, that's A plus 2C. Here we have B plus 2D. Yeah, B times 1, then D times 2. Then we have 3A plus 4C. Then here we have 3B plus 4D. And all of that is equal to 1, 0, 0, 1, like that. So what are we going to do with this? Just multiply out, okay? Just equate 10 by 10. So this is equal to this, for instance. So you have A plus 2C equals 1. Then another, it's A plus, so 3A plus 4C equals 0. This one now. So you can solve this simultaneously. So of course, we know that this is the same thing as uh well, I think elimination is sweeter, if you ask me. So this is equation 1, this is equation 2, if you like. So we can say equation 1 multiplied by 2. So that way we can eliminate C easily. So we have 2A plus 4C equals 2. And down here, we have, so equation 2 multiplied by 1, we keep it so that 4 can cancel 4. So that's 3A plus 4C equals 0. So we can then subtract, okay? We can subtract. So 2A minus 2A, or if you take it up, so 3A minus 2A, that is A. 4C minus 4C is gone, right? So, and that is 0 minus 2, that's minus 2. So we see here that A is equal to minus 2. We keep that. So now that we have got A, we can easily get C. So from equation 1, so we can say from 1 now, from equation 1, we have A plus 2C is 1. A plus 2C is equal to 1. Now A is minus 2, so we have minus 2 plus 2C is 1. That means 2C is equal to 1 plus 2. Okay, so C now is equal to 3. 2C is 3, so C is 3 over 2. So we have C already. So to get the other ones, what do? We go again for B plus 2D is 0. So b plus 2d is equal to 0. Call that equation 3. Then 3b plus 4d is equal to 1 now. This one here. So term element by element as they correspond. So here we can also eliminate. So I can say equation 3 multiplied by 3 because I want to eliminate b. You can also eliminate d. Anyone you want to eliminate is fine. But I'm just showing that you can do anyone you like. So equation 3 by 3. So you have 3b plus 6d is equal to 0. That's 3 times b, 3b, 3 times 2d, 6d, 3 times 0, 0. Then you cannot do equation 4 times 1 because you want to eliminate 3b now. So you keep that 3b plus 4d equals 1, right? So you can then subtract again because they all have the same sign. So you can then just subtract. So if you subtract this now, you have 3b 3b minus 3b, 0. 6d minus 4d, that's 2d. Then 0 minus 1, that's minus 1. So you see that d is equal to minus half, okay? D is minus half, so we keep that. So, and then lastly, we have, so now that we know d, we can actually get D is minus half, right? So we can get C, and we can get B. So we can say from 3. So from 3, equation 3, we know that B plus 2D is equal to 0, right? B plus 2D is 0, this. So, and then we have D to be minus half. We have B plus 2 times minus half equals 0. So that's B minus 1 equals 0, right? Because 2 cancels 2 here. So that means B is equal to 1. All right. So with this in place now, we can then say, so A inverse is equal to, how did we put it? A, B, C, D. So A is minus 2. Okay, minus 2. B is 1. C is 3 over 2. C is 3 over 2. And D is minus half. Okay. So does it look familiar? Sure does. Minus half. So you remember we found this inverse the other time using Wolfram alpha. That's minus 2, 3 over 2, 1 minus half. Oh, sorry. The inverse is minus 2, 1, 3 over 2 minus half. Okay, like this now. Okay, minus 2, 1, 3 over 2 minus half. So that's so inverse exists. So also with that now we can then conclude that this set of matrices, right? So the set, the this the or we can just say therefore, right? Therefore, therefore, GL sub n of R, that is the set of all invertible n by n real matrices with the operation of multiplication is a group. We have proven that much right now. So, and that is exactly what this is telling us right here, right? So we have that taken care of. So, we say closure is obeyed, associativity, identity, and inverse, all there. So this is actually a group. So it is important that the set of all n by n matrices is not a group under multiplication because singular matrices do not have inverses, right? Now, you see, this is only possible for all invertible n by n real matrices, but not all n by n matrices is not a group under multiplication because singular matrices do not have inverses. So any matrix whose determinant is 0 is non is singular and it is non-invertible. So for those kind of things, you cannot say they are groups. Okay, so I mean I've done something like this now. So let A be 1, 3, 2, 4. So you compute the determinants. So the determinant is 4 minus 6. That's minus 2, which is greater than 0. So it is invertible. So you can find the inverse of it. Then it can follow that rule now. So for A now, so you have A, B, C, D. The inverse is computed as 1 over AD minus BC into D minus B minus C over A. Now, another approach is what I've used over on the worksheet where I just left A inverse blank and then try to get the values of A, B, C, D. That's another way to do it, but this is another way to do it too if you are very good at memorizing formulas. And it's also derivable for sure. So thus you can see that A inverse is 1 over minus 2 which into 4 minus 2 minus 3, 1, and then you have minus 2, 1, 3 over 2 minus half, just like what exactly I got over here the other time, right? So we have all of that. So you can verify that A inverse is equal to I, and A inverse A is also equal to I by multiplication. Of course, we can check that out, right? So, so we know that A inverse, or I mean A inverse is equal to I like this. So you can check that out. And how do we do that? A itself, right? A is 1, 2, 3, 4. A is 1, 2, 3, 4, right? So we have 1, 2, 3, 4, and A inverse is 1 minus 2, 1, right? Minus 2, 1, and then 3, 2, 3 over 2 minus half, like this. So you want to check that to see that it's actually like that. So we have minus 2, 3 over 2, all right? And then we also have minus 2, 3 over 2. Then we have 1 minus half, and then 1 minus half. Then you can put all these ones over it. 1, 2, 1, 2. So you have 1, 2, 1, 2. This is 3, 4, 3, 4, right? So this is A inverse, right? So A inverse now can be equal to minus 2 times 1, that's minus 2. 3 over 2 times 3, that's plus 3. Then down here, minus 2 times 3, that's minus 6. 3 over 2 times 4, that's 2 goes in 4, 8. 3 over 2 times 4, that's 3 goes in 4, 8 times 8. What's that now? 3 over 2, right? 3 over 2, yes. So this is 3, 4, 3, 4. So 3, 4. Minus 2 times 3 is minus 6. 3 over 2. 2 goes in 4 twice, okay? So 2 times 3 times 2 is 6. So you have plus 6 here. Then 1 times 3. I mean, up here, 1 times 1 is 1. Then minus half times 2. That's minus 1. Then down here, 3 times 1 is 3. Minus half times 4. That's minus 2. And then we simply just have 1, 0, 0, 1. So you can see that A inverse is actually the identity matrix, as we have that. So if you also go A inverse A, it's the same thing. So let's talk about abelian versus non-abelian groups. Okay, so a group G comma star is abelian if A star B is equal to B star A for all A B in G. So if there exists A B in G such that A star B is not equal to B star A, then the group is non-abelian. So examples, you have Z comma star is abelian, of course, for any two. Z is the group set of all integers, right? So if you pick any two integers and add them together, you get another integer, correct, for sure. Then for rational number, all rational numbers take away 0. So for if you pick any two rational numbers apart from 0 and multiply, you get another rational number. Then for this one now, for the set of all invertible n by n real matrices, they are usually non-abelian for n greater than or equal to 2. Now, the reason for that is that AB is not necessarily equal to BA, as you can see here now. So you see, we have 1, 1, 0, 1 and 1, 0, 1, 1. So if you compute this, you get 2, 1. I mean, I've already explained how to multiply. So you have 1, 1, 1, 1, 1 1 twice, 0 1 0 1 twice. So it's like 1 1 times 1 1. So 1 times 1 1, 1 times 1 1, that's 2. Then for the other side, 1 times 0 0, 1 times 1, you have this one here. For this other one, so 1 1 down here. So you have 0 1 times 1 1, that's 1 here. Then 0 1 times 1 1, you have another one here. So you see that. But when you come here now, you have 1 0 times 1 0, that's 1 here. Then 1 1 times 1 0, you have 1 again. Then for this 1 1, you have 1 0 times 1 1, you have 1. Then 1 1 times 1 1, you have 1 times 1 times plus 1 times 1, that's 2. Okay, so you see this is 2 1 1 1, whereas this is 1 1 1 2. So you see that AB is not equal to BA, and that is why matrix multiplication is non-commutative. So since AB is not equal to BA, multiplication here is non-commutative. So this matrix group is non-abelian, right? And then we come for cancellation laws. So for cancellation laws now, in any group G comma star, left cancellation, you have left cancellation. If A star B is equal to A star C, then B equals C. That is left cancellation. Then right cancellation is exists if B star A is equal to C star A, then B is equal to C. These are guaranteed because every element has an inverse. So every element has an inverse. So how do we prove all this now? So if you want to prove left cancellation, for instance, so you assume that A star B is equal to A star C. That's our assumption, right? So multiply on the left by A inverse. So you have A inverse star A star B here, then A inverse star A star C. So you put A, B together. Then if you use associativity, you can move the brackets to cover A star and A. So you have A star B. Same here, A star, A inverse star A star C. So if you put this together, A star A times A, you have identity element. So at the end of the day, identity element times B simply gives you B. And that is also equal to A inverse times A, which is also identity element times C. So at the end of the day, A star B is B, A star C is C. So use the identity property and you get B equals C. So left cancellation holds in every group, right? So, and that takes us to the idea of the uniqueness of the identity element. So for any group, the identity element is unique. So we have our claim, a group has exactly one identity element. So suppose E and F are both identity elements. So because E is an identity, all right, we can simply say that E star F is equal to F. Now, because F is an identity too, right? We can say E star F is equal to E, simply. So in that case, now we just see that we can simply conclude that E is equal to F. So the identity is unique. So here we have tried to prove this claim by using a counter, what is that thing called now? By contradiction. So we have already said that a group has exactly one identity element. But if you now say suppose that E and F are both identity elements, we are now trying to say that our initial claim is not true. That means we are going by contradiction. But at the end of the day, we discover that okay, even if they are different, right, they're actually the same. E is equal to F. So it's actually unique at the end of the day. Then we also have the uniqueness of the inverse, which is it proven very sweetly. So our claim is each element in a group has exactly one inverse. So if you say let A belong to G and suppose B and C are both inverses of A. So let's assume B and C are inverses of A now. So it means if you multiply A by B, you should get the identity element. If you also multiply A by C, you should also get the identity element. In the same way, if you multiply B by A, you should get the identity element too because B is inverse, right? If you assume that. So if you compute all that, you discover that B is actually the same thing as B times E, which is the identity element here. B times E is still B. And then you know that E here is A times C. So you can put that, all right? And if you use associativity, you can move the bracket to cover B and A. So you have B times A, which is actually an identity element here, like here, because B times A is also E. So we now have E times C now, which is also C. So you see at the end of the B is equal to C. And that establishes the fact that each element in the group has exactly one inverse. So if you assume there are more than one, they end up becoming exactly the same. So B equals C, meaning the inverse is actually unique. So we have a quick summary checklist, okay, for group axioms and examples now. So we see first of all that a binary operation in S is on S is a rule star, which maps S to S to give us S, and that tells us that closure is required. Then we have a group G, comma star satisfies closure, associativity and identity and inverses, right? So for a set and a binary operation to be a group, then it must satisfy all these laws. Then you have Z, the group of all integers under addition is an abelian group with identity 0 and inverse of A equal to minus A, which I also told you about. Then Q star, which is the group of all rational numbers, take away 0, is under multiplication is an abelian group with identity 1 and inverse of A equal to 1 over A. We proved all of that. Then you have GL sub n of R, right? Under multiplication is a group of invertible matrices, and it's typically non-abelian for n greater than or equal to 2 because AB is not equal to BA. That's talking about matrix multiplication. Then groups satisfy left and right cancellation, which we showed up there just now. And identity and inverses are unique. Did I even show the proof for the cancellation thing? Yeah, I think I did that. So what you did for left, you can do for right too, basically. So here we have some practice questions. So I'm going to solve the first question, right? And then I'll just leave you to try your hands on the rest. So here now we have S to be Z, the set of all integers, and we define A star B to be A plus B plus 1. So we need to prove that it's a binary operation on Z. What we need is basically the idea of closure. Then we need to find the identity element for star, all right, and find the inverse of an arbitrary A, which belongs to Z under star. So let's go for that. Let's see how that works. So here now we are saying that for Z, right, for Z, okay, with star such that star is the such that A star B is A plus B plus 1. Okay, what's the first question is to prove that star is a binary operation on Z, right? So to prove that star is a binary operation on Z. Okay, so to prove that this operation is a binary operation on Z, binary operation, okay, on Z. So what do we need to do? We need to show. So show that it is closed. Simply, that's all we need to do. We need to show that it is closed. So again, we have A star B equals A plus B plus 1. So we know, take any integer. So we know that for all A and B, any two integers you pick belonging to Z, right? We know that A plus B plus 1 will always be also in that, will also be an integer. So pick any two integers, anyhow you like it. 10 and 50, that's 60 plus 1, 61. It's an integer. So that one is closure is set. So star is closed. Star is closed on the set Z. Basically, that's the first thing we have to do there. That's the A part. Now, for the B part, right? For the B part now, the B part is to the B part, find the identity element of for star. Okay, so to find the identity element for star, okay, to find the identity element, for the operation star. So we need to we need to show that for any element you pick, we need to show that A identity element, right? So we need to show that A star E is equal to E star A. That is always equal to A, right? So that's what we need to show right there. So in this case now, we are saying that of course we know again that A star B is equal to A plus B plus 1. So what that simply means is that if you now have A star E, that should be A star E plus 1, right? And that is equal to 1. I mean, that is equal to A right now, okay? Or if you like, you can also do, the alternative is to say E star A. That is E plus, oh, so not star here. E plus 1, all right? E plus A plus 1 is also equal to A. So anyhow you want to do it, it's the same thing. So for this now, so A star E implies that A plus E plus 1 is this. So if you want to do this now, so you have E plus 1 is equal to A minus A. All right, so E plus 1 is simply 0. Okay, that means the identity element is minus 1. So the identity element for this particular operation is minus 1. Then now we find the inverse of an arbitrary A under belonging to Z under star. Okay, so to find identity element, I mean to find inverse, right? Is it inverse you're looking for now? Yeah, find the inverse of an arbitrary A. So basically to find the inverse, okay, we need to show that what's that now? We need to show that A star A inverse Okay, A star A inverse is equal to A inverse. Okay, well, we need to show that A star A inverse is actually A plus A inverse plus 1, and that is equal to minus 1. That's the identity element, the E, which is minus 1. Okay, we can either show this or show that A inverse star A is equal to A inverse plus A plus 1, which is also E, and that is minus 1. So anyone you pick is fine. So let's pick the first one. So let's pick this first one now. Okay, so we have A plus A inverse plus 1 equals minus 1. So we are looking for this A inverse now. So we have that we have that A plus A inverse is equal to minus 1 minus 1. All right. So that is A plus A inverse equals minus 2. So that A inverse itself would be equal to minus 2 over A. So that is the inverse for this particular case. It is minus 2 over A. So if you pick any number in that set, so if you pick like 7, okay. So for 7, so, I mean, I'm just giving an example. So I say, so for 7, uh, A inverse will be minus 2 over 7. That's what that is about right there. Because if you add these two together, now you're going to get the identity element. That's 7 minus 2 over 7, right? 7. Oh, okay. Now that's my mistake right there. I'm making a serious mistake. I'm dividing when I should be subtracting. My bad. Okay. So we are looking for A inverse. So A inverse is equal to minus 2 minus A. That's A inverse is minus 2 plus A like this. That is A inverse, sorry. So thank God I did that example. So for 7, the inverse is minus 2 plus 7, which is equal to minus 9, right? Because if we operate that together, we should get the inverse. What's the inverse again? The inverse is, uh, we should get the identity, right? The identity is minus 1. Okay. This is minus 1, minus 1. Yeah, that's minus 2. So A inverse is minus 2 minus A. That's minus 2 plus A now. So that's minus 9. So 7 minus 9 is minus 2. Oh, that's not the identity. Hope I didn't make a mistake here. So A plus E plus 1 is equal to A. That's what identity means. So we have that E plus 1 is A minus A, which is 0. So E is minus 1. I think that should work. So this is minus 1, right? I hope, what did I do wrongly? So A plus A inverse, A plus A inverse plus 1 is equal to minus 1, yes. So that we now have, so minus 1 minus, that's minus 2. So A plus A inverse is equal to minus 2, yeah. So A inverse is minus 2 minus A, which is minus 2, minus into 2 plus A. So for 7 now, the inverse should be minus 2 plus 7. So that's minus 2 minus 7, that's minus 9. So if we add these two together, okay, I think I get it now. So if you now have, oh yeah, I get it. It's fine. So 7 star minus 9 now is actually 7 plus minus 9 plus 1, right? That is 7 minus 9 plus 1. So 7 minus 9 is minus 2 plus 1 is minus 1. Yeah, we are good. So this is actually fine. So that's how that is. So please try out the other questions and see if you can try your hands on them. These are the first 5, okay, and then you have the other 5. So try your hands on them and be sure you actually get the gist like that. Okay. Yeah, so let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have not subscribed already, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Ultimately, you can become a member of the channel by clicking on join. Then ultimately, you can become, you can actually be sure to share the video, comment, like, and share so that more people can have access to this great content I have going on here. So, like, come your way again. Keep doing maths right. Bye.